So we have seen that the forward checking algorithm was not able to detect all the possible inconsistencies. Okay? And we will find a solution to make sure that we would be able to detect as soon as it's possible that there is no feasible solution to the all different constraints. This is what we mean by the consistency check. And we have a very nice solution for that that was proposed by Jean-Charles Régin in 95. And the idea is to cast the problem into a graph problem. And to do that, we will create what we call the graph of variables values. It's a bipartite graph. We will put on the left all the variables and to the right all the values. And we will add an edge in this graph, in the bipartite graph, if the corresponding value belongs to the corresponding variable. So for instance, if you take the variable 0 here, it has two values, 3 and 4. And so it means that starting from the variable 0, we will add an edge to the value 3 and we add an edge to the value 4. Okay? Okay, then you will tell me, what do we gain by doing this bipartite graph? The gain that we have is that we have a perfect solution now to detect inconsistency for the all different constraints by using what we call the matching, the matching algorithm in graphs. And so the theorem that we will use is this one. We have a one-to-one correspondence between the matching problem and the fact that there is a solution for the all different constraints. We can find a maximum matching of size of the cardinality, so the number of edges involved in this matching is exactly equal to the number of variables in the all different constraint. If we can match a matching, it means that we have a solution for the all different constraint by construction. Okay, so if you remember, what is a matching? A matching is a set of edges in the graph so that they don't have a common incidence. So you cannot have a situation like this one in a matching. Okay, if I take the general graph like this one. Okay, let's take this graph. Create a matching. If you select that edge, then you cannot take this one, for instance, because it would have a node that is incident for both edges. But you can take this one, and you could take, so if you take that one, let's come back. So if you take this one, you could take, for instance, this one, and that's it, right? You cannot select this one, you cannot select this one, you cannot select this one anymore, not this one, not this one, okay? And a maximum matching is a matching in which you select the maximum number of edges. And what matters here, because it's a bipartite graph, is that the matching touches every variable in the all different constraint. Because if the matching touches every variable in my constraint, then I have a solution, of course. Okay, and it's easy to find. You just have to follow the blue edges. So x0 will take the value 3, x1 will take the value 1, x2 will take the value 4. Okay, and we know that they have all different values because they don't have common edges. So we cannot have two variables taking the same value with this maximum matching. Then you will tell me this is fine if it's true that if we find a maximum matching of size equal to the number of variables, then we have a solution for the all different constraints. But how do we find such a matching? And this is what I will just explain, is how to find such a matching efficiently, and can we find it in polynomial time? And the answer is yes, we can find it in polynomial time. This is how it works to discover a maximum matching. You will start with a suboptimal matching and you will gradually improve it step by step. So you can start with any maximum matching. You could start just with a matching with just one edge, which is obviously one that is a feasible one, and then you can greedily augment it. What I propose is to do it a little bit better than just starting with one edge. We will start with a greedy assignment of the variables, and every time we'll take the first value that is still available. So we will go in that direction. And we start with x0, we give the first value that is available, which is 3, okay, we assign it, and we will never reconsider, we will never reconsider it again. So x0 takes 3. Then we have x1, we take the first one, okay, we always consider in that direction for the values as well. So the first one is x1, we take it. x2, okay, we see that x3 is already taken by x0, so we go to the next, we give it 4. You see here? Then x3, the first one available is x0, it works. x4, we give it 5. x5, already taken, so we give it 6, which is still available. Then x6, we give it 2, which is the only one available. It's not yet taken by any other variables. We have x7, we give it 7, which is still available. You see that the previous ones are already taken by other variables. And then we come to x8, and we have a problem here, because you see that all the variables in the domain of x8, which are 5, 6, and 7, are already touched by some edges in the matching, and so we don't have a solution for x8. Okay, so the greedy algorithm that I just proposed fails to discover that the constraint is feasible, but it surely doesn't mean that there is no maximum matching here. This is just the initialization of the global algorithm that I will explain, and now we need to augment to improve this matching unless we find that there is a condition that proves that we cannot improve it. Okay, that's the idea. So how do we improve this matching? The idea is that we will orient the edges. We will orient the edges, and instead of an undirected graph, we will make it a directed graph. And the way it works is that we will put the blue edges, we go from the left to the right, from the right to the left, and the white edges will be oriented from the left to the right, exactly like this. Okay, this is the only transformation that we do. And then we will do a depth first search starting from this node here, and we will try to find an alternating path. An alternating path is a succession of edges that are not in the matching, and then in the matching, not in the matching, and in the matching. And since you have correctly oriented the edges, the maximum, any path that you would find will always be alternating. You see, because you will always go from the left to the right, and then from the right to the left. And the only way to do that is to take a white edge and then a blue edge. So you will always do white, blue, white, blue, white, blue, white, blue, like that. And if you can find an augmenting path starting from here, and that would finish somewhere here, okay, hopefully in something that is not yet taken, then you can just flip the status of the edges. The one that were not in the matches on this path will be in the matching, and the one that were already in the matching will be removed from the matching. Okay, and so we have found, if we can find such an alternating path, it means that we were able to improve by at least one additional variable. We were able to improve by 1 the maximum matching. We do that until we meet the condition that we are not able to find an augmenting path. And so in that case, we can stop and we can claim that this is the maximum matching. And if this maximum matching is less than variables here, then we can stop. We can stop and we can say that the constraint is unfeasible if the number of blue edges is less than, in this case, 9, the number of variables. Okay? So that's the way we discover the maximum matching. Again, you start with any maximum matching, for instance, an empty one or the one that were discovered with the greedy solution, and then you will iteratively improve it by discovering augmenting path. Okay, and you can do that by just orienting the edges and then use your favorite depth first search algorithm to discover augmenting path. And then you can stop whenever there is no augmenting path. Okay. So now we have the maximum matching, and we know that the constraint is consistent because all the variables are incident to a blue edge. The next very important question is, which edges can we remove from the domains of the variables? Okay, because it doesn't mean that it's consistent, that there is at least one solution to the different. It doesn't mean that we will not be able to remove inconsistent edges. Okay, and the goal here is really to do the same reasoning as a Sudoku player would do, but we need to put that into equation and into a nice algorithm, and this is what I will explain in the next video.